Hello and welcome to this video on the HVAC refrigeration cycle, one of the beginning level video series at MEP-Precon.com. My name is Ken Dykman, and make sure that you jump over to our website if you found this video on YouTube to take the assessment at the end of this to make sure you understand all of the concepts in this video. This is going to be a high-level video mainly for newcomers in the industry that answers the question of, when you plug in a device, an air conditioning system, how does that work? How do you produce cooling? How do electrons flow through this power cord and produce cooling on the other end? I know that was it took a long time for me to get those concepts. There's some pretty big concepts in the refrigeration cycle, and we're going to go through all of that today, so that if you've never had any exposure to how cooling is made within the refrigeration cycle, you will understand it after this video. All right, so the objectives of this video is not to become a technician and be able to troubleshoot a refrigeration cycle or an air conditioning system within an HVAC unit. It's mainly just to identify the parts of refrigeration, the role of each, the bare minimum parts, that is. There's quite a few other parts. We're just going to talk about 6. You need to have 6 components to a refrigeration cycle, and we'll talk about that. There's some fundamental thermodynamics basically behind refrigeration that we're going to talk about, with pressure and temperature, and then we'll go through the refrigeration cycle and understand how cooling is made, and talk about different compressors too, because in the HVAC industry you'll hear a lot about different types of compressors, so we'll look at those and how they work. All right, so let's jump into some thermodynamics first, because it's really important to understand some of these fundamentals. And if you've taken a high school or a college chemistry class, great. If not, no big deal. Don't worry, we'll walk through it, and we'll bring you along here. So to understand this whole concept of the refrigeration cycle, you need to understand a little bit about just plain old heat, what heat is and heat transfer, and also pressure. And we're also going to be talking about this perfect gas law, which is discussed in thermodynamics and a little bit in chemistry as well. And let's talk about heat first of all. So if you're not familiar with the concept of a BTU, a British thermal unit, let's talk about that first, because you'll hear about that a lot in our industry, as well as these videos here. So a British thermal unit is the amount of heat that it takes to raise 1 pound of water, what do you think, 1 degree Fahrenheit or Celsius? 1 pound of water, 1 degree. It's Fahrenheit because it's British thermal unit. And so yeah, the British were the ones that invented the system that we use, feet and inches and miles and Fahrenheit. And then they gave it to us, and they went off to use the metric system like the rest of the world. So we're stuck with the English system. So we use terms of BTUs. And to conceptualize a little bit about how much a single BTU is, it's about as much heat as contained within a single matchstick. And so think about that, and that might be logical, that if you had a cup of maybe 10 ounces of water or so, whatever a pound is, and you held a match underneath it until it burned out, yeah, swirled it around a little bit, it probably would heat it up by about 1 degree Fahrenheit. And then 12,000 of those BTUs is what we would call a ton of refrigeration, or a ton of heat within the HVAC industry is 12,000 of those matchsticks basically burning at once. All right, so understand a little bit about BTUs and heat here. BTUs can travel through walls. One of the ways to understand the concepts of HVAC is to imagine yourself as an air molecule or a water molecule traveling down a duct or a pipe, because really HVAC is all about fluid flow, either air or water, and heat transfer. BTUs transferring from one fluid to another through a heat exchanger. And so through a heat exchanger, the two fluids, if it's air or water, and there could be water to water, or it could be refrigerant to air or refrigerant to water, those stay on both sides of the heat exchanger. They never come in contact with each other. But the BTUs, they can go through the walls of the heat exchanger. Those little heat, if you can think of a BTU as a molecule, it's not really a molecule. It's just the excitement of the heat within the water or the air that moves around a lot faster. That's essentially what heat is. It's the rapid movement, how much movement those molecules are within, basically, or undertaking, how much movement that is. That's the level of heat within a fluid that way. But BTUs can travel through the walls of a heat exchanger. And then, let's see, you need to understand that heat travels in fluids and solids more efficiently than in air. And I think that's fairly intuitive. If you were standing outside in a 90-degree environment, yeah, it would be warm. It would be uncomfortable a little bit, to the point where you'd be sweating, but you could stand to be out there for a while. If you were in a 90-degree hot tub, however, you probably wouldn't be in there for much more than about 10 or 15 minutes, because 90 degrees is pretty warm. And there's just a lot of heat transfer that takes place, more so in water than in air. And you'd get sick to your stomach and so forth, much more than just standing out in a 90-degree day. So understand that if you touched a warm object, that's a solid, that conducts heat a whole lot better. So solids the best, liquids, next best, and then air. Yeah, heat transfer doesn't work as well as air, as in solids and liquids. And then what direction do you suppose heat transfers? Does it go from cold to hot, or does it travel from hot to cold? Think about that a second. The rapid movement of molecules, does that happen if you just had a hot device? Does it go from hot to cold, or from cold to hot? Does the hot device, does it attract heat from the cold? Yeah, I think you probably, talking through that, I think you probably understood that. It flows from hot to cold. And think about that intuitively. It's similar to, just us in nature, essentially. So think about when you're really hot. If you've done a lot of exercising, perhaps maybe you've done some running or some kind of a workout to where you're really hot, what is it that you naturally want to do? Well, you probably don't naturally want to do more work and get more hot. If you saw, a nice chair, perhaps in a cool environment, you'd say, oh, that's for me. I want to sit down in this cool chair. I want to relax for a little bit. I want to cool down. Well, BTUs are the same way. BTUs, they want to go from a hot environment. They're not happy in a hot environment. They want to go to a cool environment. So if they see a cool environment, that's where they're attracted to. So they're just like people. That's just the way nature works. All right. So there's something about heat there. Let's talk about pressure a little bit. So what happens to the boiling point of a liquid when pressure changes? Well, they're proportional. And so as you go up in elevation, as this little graphic shows, at the top of Mount Everest, the pressure is a little bit less there, and so the boiling point is quite a bit less. So liquid wants to naturally evaporate into a gas, and that's due to this thermodynamic property called entropy, which is pretty fancy. You can Google that if you want, but it basically says that matter wants to go from an organized state to a disorganized state, and gas is a much more disorganized state than liquid, and liquid is more disorganized than solids. So it wants to go in that direction. But in order to do that, though, it'll do that naturally to some degree in our environment, but you can increase that by heating it up. And so at sea level, the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. But as you go up in elevation, what happens is there's less pressure. And so literally within the atmosphere, there's less gravity pushing down those air molecules within the atmosphere, pushing down on the surface of the water. And so with less pressure that way, it's easier for that water to turn into a vapor. I mean, think about that, going all the way up to space. If you had, probably never seen this anywhere, but you can probably conceptualize this. If you had a jar of water, and if an astronaut was on the moon and took the lid off, what do you think would happen to that water? Yeah, it would immediately flash to a vapor because there's just no pressure. There's no gravity forcing air molecules down on the surface of that water, keeping it into that organized state. It would immediately go into a disorganized state. Even without any heat, it would just immediately flash to a gas that way. So less pressure means it's easier to boil. And then more pressure, as you can see on the other side of that graphic, is if you get below sea level, that there's more gravity pushing down on those air molecules to keep that water in that liquid state. So it's going to be harder. It's going to take more heat to boil that. All right, so there's a couple of important concepts that we need to understand there. So now let's talk about how pressure and temperature are related. And they're related in this formula called Boyle's law, or this perfect gas law. It's stated as a perfect gas law. No gas behaves this way exactly. A perfect gas is kind of a theoretical thing, but most gases behave similarly in this way. So the formula here, within a closed system, meaning that there's nothing that can escape, is this PV equals nRT. Let's talk about these variables here. So P is the pressure, V is the volume, so that's on one side of the balanced equation here, and then on the other side is N, and it really in chemistry this is referred to as the number of moles, but it's essentially the number of molecules within the system. R is just a constant in order to make the conversions, the unit conversions to work out properly within this equation. And then T is the temperature of what's inside that closed system there. And so if everything else is held constant, the volume, the number of molecules within a system, but as the pressure goes up, what happens to the temperature? Yeah, if everything else stays constant, the temperature goes up too. And as the pressure goes down, the temperature goes down. So based on that, looking at this little diagram here, what do you think is true for a gas then? Which one of those would be true? Look at them and take a look there. So let's take a look at number 2. Number 2 says as the temperature varies, the pressure stays the same. Well, we didn't talk about that. Here it says as the temperature stays the same, the pressure varies up and down. Well, that doesn't happen either. And then here, this is kind of a logarithmic curve. Yeah, that's something weird's going on there. But yeah, number 1 is the right answer here. And so that represents the direct linear equation that we just talked about, the PV equals nRT. So as temperature increases, everything else is held constant. If the temperature increases, the pressure increases, and it's linear. It's not P squared is proportional to T or P cubed or anything like that. It's pressure and temperature, so that means it's a linear function. It's not a quadratic or a logarithmic type function like this would show. All right, I think you got those concepts down. If not, feel free to rewind it, look for some other resources on the internet, but it's really good to understand those fundamental concepts before we get into the refrigeration cycle here. Let's talk about the different types of heat real quick as far as sensible and latent heat. And so when matter changes state between a solid and a liquid, meaning melting, if you take water, for example, from melting from ice to a liquid, or from a liquid to a gas when it boils, there's a lot of latent heat within that phase change. And if you took a chemistry class, you might have done this experiment, but if not, you could try this at home. You could take a container, maybe a pot of water on the stove, and especially if you have a gas stove. If you have an electric stove, this may not work too well because electric stoves, the element tends to cycle on and off. You know, for whatever setting that you have, it tends to cycle on and off. But if you have a gas stove, this would work really well. So put room temperature water in there, or whatever the water temperature is that comes out of your faucet, and then put a candy or a meat thermometer in that water and let it heat up to where it's going to boil. And what you would see, let me get my laser pointer operational here. So here is the liquid here between ice and between gas. This is all liquid. So as time goes on and you're adding heat to that water, it's going to increase in temperature. Here's temperature in our y-axis here. So as time goes on, it's going to increase in temperature until it gets to about 208, 209 degrees Fahrenheit. And then at that point, it's just going to sit there for a little bit. It's going to sit at this constant temperature. As time goes on, you're continuing to add heat, maybe from that gas stove. And then eventually, after some time, at that point, it's going to start boiling. And so you could literally make a graph and demonstrate this for yourself. And so that additional heat that's added to the liquid before it boils, that's called latent heat. Or specifically, it's called the heat of vaporization, and this is the heat of fusion, when that's the latent heat between a liquid and a solid state. And so that's important in refrigeration because we have a lot of phase changes happening, and within that phase change, there's a lot of energy that can be released within that phase change. Sensible heat is the heat that you can actually feel. So within this area here, the difference in temperature that you can actually feel that makes a difference, that's sensible heat. And then the latent heat is the heat that you can't feel, but it gets added to a substance, when it goes from one phase to another. All right. Phew, that was a lot. So let's put those concepts together now within the HVAC refrigeration cycle. So in order to make cooling within a refrigeration cycle, you have to have 6 components. This is a bare minimum. And remember in that first graphic that we had at the beginning of this video, there was a lot of other components in there for smooth operation, for automatic operation, for energy savings, but we're just going to focus on these 6 components. You have to have these 6 components as a minimum in order for the refrigeration cycle to work. You have a condenser, an evaporator. These are 2 heat exchange devices. You have a compressor and an expansion valve, and these are 2 pressure devices. Then you have piping that connects all of those components together. And then finally, you have a refrigerant that flows within the piping that goes through all of these components. And that's it. That is all that you need really in order to have a refrigeration cycle. Let's talk a little bit about refrigerants though, and properties of a good refrigerant for a refrigeration cycle. So one of the big concepts that is really hard to grasp is that a good refrigerant for an HVAC system is something that is a liquid that boils at a very low temperature. I'm talking around 30, 35 degrees or so, maybe even lower than that. Depends on the system, it depends on the refrigerant. There's lots of different types of refrigerants out there. But yeah, it's going to boil at that temperature. And we manipulate it with some pressure and so forth too, because remember, pressure and temperature are related that way. So we manipulate it such that it can boil at a very low temperature. And that's a really hard concept to grasp because we think that, well, at 30 degrees, it should be freezing. Well, that's water, but refrigerant is a totally different substance, and that refrigerant at that temperature is going to boil. So understand that concept, make sure to really fix that in your head there as we go through this refrigeration cycle here. It has a low boiling point. It has a much lower freezing point. Obviously, we don't want it to solidify within our piping or within those components. It needs to be non-toxic, such that if we have any leaks within a building, it's not going to be harmful to the occupants that way. And we could have leaks because sometimes there's going to be a lot of joints within a building, and sometimes settling or something might create a leak. So it's really important that it's not flammable or it's not toxic to people. About the only refrigerant out there that's toxic could be ammonia, and those are typically not used within HVAC systems where they'd be exposed in the airstream. Those are typically reserved for ice plants because we need a really low temperature there to get the surface of a concrete slab cold enough to freeze water. It needs to have a high latent heat capacity, between phase changes so we can capture that energy, and non-corrosive so it's not going to rot out our piping. And oftentimes refrigerants are a mix of different types of chemicals, so we want it to stay mixed and stable. We don't want it to separate within our system at all. All right, so let's put all those concepts together and let's walk through a schematic of a refrigeration cycle. We're going to stay here for a little bit here and walk through what is happening with the refrigerant as it goes through all of these components. And so let's look at these components again here. So we have two heat transfer devices. We have an evaporator and a condenser. And let's think of these as air coils. If you're familiar with an air coil, kind of like the radiator of your car, if you've ever seen that. If not, open up the hood and take a look at it. It's in the very front, but water flows through the little small tubes that you can see in the radiator, and then on the outside of those tubes are connected, solidly connected to those tubes are some fins. So there's some heat transfer that takes place between the water and the air within that radiator. And that's what keeps your car cool, because you're burning gas, you've got flames within your engine all the time. You got to keep that cool, so we circulate water in your engine. And as air blows through that radiator, it removes the heat off the water that way. There's heat transfer that takes place within the fins. This works very similar within let's call this a packaged air conditioning unit. We're going to be in air conditioning mode here. We're going to talk about that for the majority of the rest of this video. At the very end, we'll talk about a heat pump. But for right now, let's talk about air conditioning, meaning we're going to remove heat from the building. And we're going to do that with an air coil here. On one side of this coil is refrigerant, and on the other side is air. Same thing with the condenser. So two heat transfer devices, and then two devices that control the pressure. And as you're going to see as we go through here, we need this to change the pressure to get the temperatures in the right proportion in order for heat transfer to take place. Okay, let's walk through it here and see what happens. So I can start anywhere here, but I'm going to start down here in this corner just because that's how I set this up here. So the refrigerant in this corner here is going to be at a very low temperature and a very low pressure. Don't worry about how it got in into that state. By the time you make it around, you'll understand how it got into that low pressure, low temperature state. But for right now, just assume as a given that it's in, trust me, it's in a low pressure, low temperature state. And let's talk about some temperatures. It might be 30 degrees or so. And so it's really cold, and it's going to enter this evaporator, which is the indoor coil of our air conditioning unit. This is what we blow air through in order to cool that air off and blow that cool air into our space to be able to enjoy a nice cool environment if it's hot outside, or if it's hot inside, if we have a lot of lights and people creating a big heating load. And make sure to take a look at our other video on loads and zones to understand all of the components that go into creating a cooling load, a demand on comfort that way. So that's going to heat up our environment, and we combat that with cool air. So what's happening here is as we blow air through that indoor coil that we're going to use, we're going to circulate that supply air through here. It's going to go into our space, and it's going to return back at some temperature. And we're going to remove the heat from that by exchanging that with the colder refrigerant temperature. So within a heat exchanger, there's two fluids, and one fluid is going to heat up and the other one is going to cool down because heat transfer happens across through the walls of that heat exchanger. So in this case, the return air within your HVAC system, if it's warm, it might be 80 degrees. It heats up in the room and it comes back through the return duct, goes into the unit. It might be about 80 degrees. And the refrigerant coming in here is about 30 degrees. So what happens here in this heat exchanger? Well, one fluid is going to cool down, the evaporator, as it gives off its heat to the refrigerant, and the other fluid, the refrigerant, is going to heat up. And remember how heat travels from hot to cold. What's happening in here is that hot air, there's a bunch of air molecules in there moving really rapidly back and forth. That's called heat. They're hot. And so those hot molecules, think of them as BTUs now. Those BTUs now see a cold environment, and just like you after a workout, they say, "Oh wow, I see a cold environment. I'm uncomfortable right now, moving around as much as I am. I just want to chill. I want to sit down in this nice cold chair and just sit down and relax for a little bit." So it jumps through the wall of that heat exchanger, and now it's in a much colder environment, and now all those BTUs are very comfortable. They're saying, ah, I like this. So that's how BTUs heat travels, basically from hot to cold, in kind of a cartoonish kind of a way. So that's the role of the evaporator, is to pull the heat out of the air. And at that point, we're essentially done in our HVAC system. You know, we've achieved the goal of pulling the heat out of the air so that the heat, the air coming back into our room is cooler now, and we can all enjoy a cooler room. But within this video, we're not done yet, because we want to talk about, well, where does that heat go? Because eventually that heat's going to build up. So let's walk through the rest of these components and see how we actually reject heat out of the building. Because eventually we just want to, you know, we want to get all of those heat. The building's going to heat up eventually with a bunch of BTUs from the sun coming in, the outdoor air being warm, people giving off BTUs, lights, computers, internal loads. All kinds of things contribute to the load that heats up our space. We want to get them out of the building. So those BTUs, now that we're in the space that's now in the refrigerant, it's going to come over here to our compressor. So before it does, let's talk about the state of the refrigerant. And so as it has come in here as a liquid, if I didn't mention that before, it's a liquid at a low temperature and low pressure. And as it absorbs heat, it evaporates, because that's kind of the name of this. You can kind of think of this here, the evaporator. That's the job that it does on the refrigerant. It evaporates the refrigerant. It's literally boiling off. And so now it leaves the evaporator as a complete gas. All of it is, there's no more liquid, it's evaporated all into a gas, or it's boiled off into a gas. And so, and the temperature of this now is a little bit higher, still at a low pressure. We haven't done much to change the pressure, but it's a little bit higher. It's absorbed some heat, and so that heat results in a higher temperature. Now it might be, say, you know, I don't know, 50 or 60 degrees or so, the refrigerant now. And now when it comes into this compressor as a gas, because again it boils at a low temperature, or it's 50 degrees or something now. So now we're going to take this compressor and compress it up into a very high pressure. And what happens within our perfect gas law, because this is a closed system, we're not going to leak anything out of here. So as we pump up the pressure, we're going to pump up the temperature too, right? Because pressure and temperature are on the opposite sides of that equation of that perfect gas law. And so we're going to pump up the pressure of that refrigerant such that the temperature is now really high. Oh, maybe 130, 140 degrees or more is the temperature of that refrigerant. And now it's going to go to our outdoor coil. So this coil looks very similar to our indoor coil, except it's going to exchange heat to the ambient air outside. So same refrigerant, it's got those BTUs from our space, it's got those BTUs that are really condensed now at a very high temperature, because we've increased, haven't done really anything to the heat. We've absorbed the heat. We're just changing the temperature of that fluid by increasing the pressure. That's kind of an important concept to understand, that we're not adding heat really with this compressor. Maybe a little bit of work on it, but it's the same amount of heat that we're absorbing. The BTU heat we've absorbed from the space, we're just changing the temperature of that by increasing the pressure through that perfect gas law. Okay, so the reason why we pump that up to a higher temperature is so that we can have heat transfer within our outdoor condenser coil. So outdoors, let's talk about some temperatures. The ambient air might be, say 80 degrees. It depends on where you're at in the world, but let's say you're running your air conditioner and it's 80 degrees outside. And so here's this refrigerant at maybe 130, 140 degrees or so. It sees ambient air at 80 degrees, and what do you suppose happens? Well, there's heat transfer that takes place because there's two fluids at different temperatures, and that causes heat transfer. One fluid cools down, and one fluid is going to heat up. Which one cools down and which one heats up? Well, the refrigerant is at 140 degrees or so, and it sees ambient air at, in our example, 80 degrees, and so the refrigerant is going to cool down, and the ambient air coming through this condenser is going to heat up. And so that ambient air might heat up to 110 degrees or so, 110 degrees, and this refrigerant is going to cool down to some cooler temperature. It's going to cool down to the point where it condenses. Now, the concept of condensing may not be as intuitive to you as evaporation, because we use the term evaporation a lot more than condenser. And that's essentially how we keep cool, is we sweat, and that sweat evaporates off of our skin. And in order for a liquid to move from or a substance to move from a liquid, to change from a liquid to a gas, it has to pull heat from something. You need to add heat to that liquid in order for it to evaporate. And so when we sweat, it pulls the heat from our skin, keeping us cool, and then it evaporates, and that's how we keep cool. Well, the condenser is just the opposite of that. It's the exact opposite of an evaporator. We're going to take that very moist, warm refrigerant that's in here, and we're going to cool it down to the point where it condenses back into a liquid. So what's happening in here is very similar to what happens within a cloud within the atmosphere. So in the atmosphere, there's lots of water molecules in the air called vapor, and eventually, if it cools down to the point where it can't stay in suspension anymore, it condenses out in the form of a cloud. And that's how clouds form, is now you can see those water vapors. They're not so small that they stay invisible within the air. They get so thick that they just can't stay in suspension anymore, and they form this cloud. And eventually up in the atmosphere, they collect on dust particles, and they get bigger and bigger, and that's how rain forms. That's how rain falls to the ground. Well, the same thing is happening in here with this condenser, is we're going to cool the refrigerant down to the point where it's going to rain in here. It's going to rain refrigerant such that at the end of this condenser, it's going to all be back into the form of a liquid again. It's going to be a little bit cooler too. It's going to be a little bit lower of a temperature, but still at a high pressure. Haven't really done much to change the pressure through here, but it is a lower temperature. You know, we talked about this being maybe 140 degrees. This might be 120 degrees or maybe 110 degrees, something like that, depending on lots of other conditions, the type of refrigerant, ambient air, all those variables. All right, so we're good with these three devices so far. Let me give you one other analogy to make sure you understand the concept of this evaporator and the condenser here, and I'll explain it in some terms that I'm sure that you're familiar with. So as an analogy here of what's happening within this evaporator, imagine having a pot of water on your stove, that would be a heat exchanger, and then filling it with water, that'll be our refrigerant. You put heat into it, that's kind of the heat of the air in this case, and on your stove, eventually that water is going to boil, right? And so that water, think of that water as refrigerant. That's the job of this evaporator, is to boil that refrigerant. Okay, now imagine, you've probably never done this before, so this may not be familiar, but I think it's intuitive to you. So imagine what would happen if you took a cookie sheet at room temperature and you held it above that pot of water on an angle such that the steam coming off that pot of water touches that cookie sheet. What do you suppose is going to happen? What are you going to observe when the steam hits that cookie sheet? Yeah, it's going to form some condensate, or what's going to happen is that steam condenses on the surface of that cookie sheet. It's going to form little water droplets, real similar to what happens in your shower after you turn it on for a second. If you're not directly spraying water on the walls of your shower, it just gets kind of steamy, and that steam hits the relatively cooler temperatures of the walls, and you get that little water mist or condensation forming on the walls of your shower. So that's what would happen on your cookie sheet, and eventually it would condense so much that it would drip down. It would drip down back into your pot of water, and you could kind of keep this cycle going for a little bit here. You could keep heating that water until it hits the cookie sheet, and it would condense and it would drip down into your pot of water, and you could keep that cycle going for a little bit there. It might be kind of a waste of energy, but you kind of understand how that works that way. Now that wouldn't work too long, because your cookie sheet would heat up, and as your cookie sheet heats up, it's not going to be that cold surface for it to condense on But anyway, I think you understand the concepts there. So hopefully that really drives home the concept of what's happening to the refrigerant there within the evaporator and the condenser. All right, so now we have this lower temperature refrigerant, but still pretty high pressure refrigerant. And now we're going to get to this expansion valve. And this expansion valve is essentially just a very small orifice. In fact, you really don't even need a valve at all. You could just have a very small orifice. And I mean a really small orifice. You can kind of think of this as, you know, a paint can or an aerosol can. The little nozzle at the very top, it's a really, really small hole. And the job of this expansion valve or an orifice is to really create that refrigeration effect. This is what Willits Carrier observed and patented just over 100 years ago now, when he patented the refrigeration cycle in the system, essentially, that if you push a fluid through a small orifice and change the pressure a whole lot utilizing the perfect gas law, what comes out of here on the other side is going to be really, really cold. And think about that if you've ever held an aerosol can after you've sprayed it a couple of times. If you feel that, it's colder, isn't it? And especially if you're a cyclist, a bike rider, and if you've ever used a CO2 cartridge to air up an inner tube, there's a tremendous difference in pressure there. And because there's such a great difference in pressure in that little CO2 cartridge, if you've ever done this, the first thing that happens is you get some water to condense on the outside of it, and then it gets so cold that that water actually freezes. There's actually frost on the outside of that CO2 cartridge because it undergoes such a massive pressure difference. It changes the temperature massively on that CO2 cartridge, and so it condenses the air around it and it freezes it right away. Okay, so back to here. So the refrigerant goes through that same orifice. And this is just like that aerosol can, that psh, psh. When you feel that and it cools down the can, it's going to cool down that refrigerant to a really, really low temperature, back down to about 30 degrees and a low pressure. Oh, so that's how we get to our low temperature, low pressure refrigerant. And so now that refrigerant is in a state and ready to come back into our evaporator, able to, within that low temperature, ready to absorb heat within the space again. So this cycle continues around, constantly being able to remove heat from the air, from the hot air from that room. And that's how we keep the room cool. That's all driven by the power cord that we plug in and the electrons that flow to power this compressor. It pushes, not only does it create a high pressure, but it actually, it's the means to push the refrigeration or the refrigerant through all of these components and keep this in a sustainable state to continue. And whenever this is turned on, you have constant air conditioning through this refrigeration cycle that way. You could produce a refrigerant cycle with just a bunch of aerosol cans here. You know, you could put a board across the top of the nozzles and just push down on them all and blow some air between the cans. That could be your heat exchanger. So as you do that, you're going to lower the temperature of the can, and as the air flows across it, you put a fan across the cans, there's going to be heat transfer that takes place. The cold cans is going to remove the heat from the air, and you've produced air conditioning that way. You've removed the heat from the air. You've cooled down the air. Trouble is, that's not going to last very long, because once all the molecules are out of your aerosol cans, well, that's the end of your refrigeration cycles. So all of this is in a closed system. The refrigeration is not going to leak, hopefully, as long as there's no leaks within all the joints. And that compressor drives that refrigeration to do what it does within each of these components. Each one of these things does a different job to that refrigerant, but it's all for the purpose of removing the heat out of the air within that evaporator. Whew, that was a lot. So hopefully you understand that. If you want a different way to have that explained to you, feel free to look at some other YouTube videos or Google it. I've found some other YouTube videos that are a lot more technical than that. So like I said, this is really beginner, just really making sure that you understand that if you plug something in, how do those electrons flowing produce the ability to cool the air? And so hopefully you understand that now. All right, so let's look at each of these components in a little more detail as to what they look like physically as opposed to just a schematic. So let's talk about the condenser first. Yeah, you've probably seen these. You know, if you're around commercial buildings, usually there's one or two of these things on the ground of every commercial building. This would be a condensing unit of a split system um, refrigeration or a split system HVAC system. And so the other parts to this is your evaporator would be on the inside of the building, and it would be connected by the couple pipes that you saw in the previous slide. Those would be the refrigerant pipes that connect the evaporator and the condenser here. And so this might be popular for an office building where we have our indoor condenser coil within a space like an IT closet or an electrical closet. So it might have a cooling load requirement in there 24 hours a day, 7 days a week, which is separate from the rest of the building, where you could shut down the main HVAC system on unoccupied hours, or at least go back into some setback conditions so that you're not spending so much energy to keep the building cool from a tenant standpoint, because it's unoccupied, there's no tenants in there. But the IT room or electrical closet, no, that's going to have a constant load. It needs to have heat removed from it all the time. Even if there aren't people in there, there might be people working at home requiring, the use of those servers, and so a lot of electrons flowing within those IT machines, and so it produces heat, and we need to get rid of them somehow. And so we get rid of that through a refrigeration cycle. So our evaporator might be within that room, that IT room or electrical closet, and it's going to remove the heat. That's our evaporator coil. So the BTUs from that room are going to jump into that evaporator, and it's going to come outside to our condensing unit. And if you've ever walked by here and put your hand over it when it's running, you feel that heat on it. And without knowing the refrigeration cycle, you might say, boy, I don't know what this machine is, but boy, it sure produces a lot of heat. Well, let's be clear. Let's make sure we get the right terminology here. It's not producing heat. It's not generating heat. It is moving the heat from the inside of the building to the outside of the building. This is where it's rejecting all those BTUs. So the BTUs that were generated or produced by the IT equipment inside the building, inside our IT closet, by all of those electrons flowing, the data and all those ones and zeros there, that produces a lot of heat and BTUs. So we're going to pull those BTUs out, and we're going to reject it through the refrigeration cycle in a very efficient, concentrated way. So when you put your hand over that and feel that heat, that's not the heat being produced by here. It's just moving the heat from inside the building to outside the building. So that's how that condenser works within an air system. Now you could have a condensing unit, essentially, which is a water to refrigerant. In fact, we'll talk about this in a couple of slides here when we talk about chillers. So within a water-cooled chiller, we're going to exchange heat from the refrigerant, not to air, like within this air coil type device, but within a shell and tube heat exchanger. And so within a shell and tube heat exchanger, there's an outside shell and then a bunch of tubes inside. And typically refrigerant flows inside of these tubes. It might come back in a couple of passes perhaps. And then the water flows up and down across these tubes. And that's how we have heat transfer. We have heat transfer between the water and the refrigerant. And that's how we exchange heat within a chiller. And we'll talk about that a little bit more here in a couple of minutes here. That would be used for a chilled water system that serves fan coils or chilled water air handling units perhaps. Okay, let's talk about the job of an evaporator, or what an evaporator might look like. Yeah, so these might be the devices that you see within maybe a big warehouse that stores apples, or just, perhaps a cooler of a restaurant, or, some type of big dining facility or something like that, where they're keeping the food cold. It could be a freezer or a refrigerator, but that's where we pump out the cold air, or essentially we're removing the heat from this space through the evaporator. And where does that heat go? Well, it's going to go out through pipes to the condensing unit. And that condensing unit takes all those BTUs from the space here, and dumps it out of the building, exchanges heat to the ambient air. So within the evaporator, that's where the refrigerant boils into a gas form. All right, let's talk about the expansion valve. And again, it could be just an orifice, but we use a valve because that's a little bit easier for us to be able to control certain aspects of the refrigeration cycle, like how much it's loaded up, different capacities, different sizes of the refrigeration cycle. So we can control the orifice size with a valve here. But it essentially just produces a very small opening to let the refrigerant through, and as it's pushed really hard on one side with high pressure, and it comes through this little small orifice and opens up to the same size pipe, well, as you can imagine, all of those molecules at a high pressure within this pipe coming through the small orifice and being released at a small amount of time into a bigger pipe is going to really reduce that pressure. And as it reduces the pressure, the temperature drops. And so we have that colder refrigerant able to come back to the evaporator to remove more heat from whatever the device is, if it's water or air. And that's the job of the expansion valve. All right, let's talk about compressors now. Many different types of compressors in HVAC, and you'll hear about these, and so we're going to talk about them in a little bit of detail here. So the compressor, it compresses that gas into a very high pressure and thereby increasing the temperature too, so that it's in a state to exchange heat into the condenser. So the types of compressors are for small equipment, for small what we call unitary equipment, small packaged equipment, 20 tons and less or so. There's what a scroll compressor looks like. And it's completely sealed up. So if something were to go wrong with this, kind of like the old VCRs, if you had troubles with your VCR that you had a long time ago, if you're that old, you wouldn't repair it. You would just throw it away or recycle it and get a new one. Same thing here. These are pretty economical. They're pretty small. And so if there's a problem with it, you wouldn't spend the labor to try to repair it. You would just evacuate the refrigerant, because we don't want that going into the atmosphere, and you would just recycle this and get a new compressor. You could get these up to maybe 30, 40, 50 tons. You would just get multiple of these scroll compressors. And if you're interested to see how this works on the inside, you can YouTube scroll compressor animations. There's a lot of manufacturers that have some pretty cool animations out there, but there's a piece of metal in here that's kind of rolled up like a scroll, like a scroll of the medieval times where people would write down a message on a scroll and roll it up. If you looked at it from the end, that's kind of how it looks like, is a scroll that way. It moves in kind of an oblong motion within a stationary scroll. And again, I encourage you to look at a video from some manufacturer, a scroll animation video, scroll compressor. All right, and then there's a reciprocating compressor. So the next larger type of compressor would be a reciprocating type. And if you're familiar with car engines, you might say, that kind of looks like a car engine. Well, that's how it operates. There's pistons in here, just like your car engine. And here it uses pistons to pump that refrigerant to a high pressure. And so it has little valves at the top where the refrigerant comes in, and the pistons pressurize it, and it leaves out of that chamber, the cylinder, that way. And again, you can YouTube reciprocating compressors to see those animations as to how that works. Then there's a screw type compressor. And okay, here's a nice cutaway here. So this kind of works kind of similar to like a jet ski or a something like that. If you've got that, a jet drive watercraft, where these things spin around a whole lot, and these screws, they interlock basically, or they interface, and as the refrigerant comes in, it does a really good job of compressing it at a higher pressure on the other end. These screw compressors, so these might go, the reciprocating could go up to 70, 80, maybe 90 tons. And then screw compressors, or the range for those is typically maybe 70 to 130, 150 tons, something like that. And then if you really want to get into the bigger compressors, and you could have multiples, by the way, of these, you could have multiples of these within an air-cooled or a water-cooled chiller. We talk a little bit more about air-cooled and water-cooled chillers in the HVAC parts video. So if you want to look at that, or YouTube some other videos, but I think we covered that pretty well within our HVAC parts video. So check out that for the difference between air-cooled and water-cooled chillers. But as we go up in size now, we have a centrifugal chiller, and boy, these things can go up to thousands of tons. And they're driven by an impeller within a volute here, kind of like a centrifugal pump. And if you have watched our HVAC basics video, or if you haven't, I encourage you to, we talk about the definition of centrifugal pump or a fan, meaning that the fluid that comes in and how it comes in and goes out is 90 degrees from each other. So a centrifugal fan or a centrifugal pump has the air or water coming in at it and going out at 90 degrees from each other. So same thing here with this refrigerant. Now this compressor is actually attached to the rest of the devices on this refrigeration cycle. This is a water-cooled chiller. So we're going to talk about this here in our next slide. So within a water-cooled chiller here, we have this shell and tube heat exchanger called our evaporator. And then we have another shell and tube heat exchanger over here with water. We're going to exchange heat between water and refrigerant within these heat exchangers. And how did I know which one was the evaporator and which one was the condenser here? Because they look similar. Well, this one is covered with some insulation, some Armaflex or Rubatex type like rubber foam insulation. And the purpose of that is because this is pretty cold. This evaporator barrel is going to see really cold refrigerant. And even though it absorbs heat, it starts off pretty cold and such that it's going to condense, it's going to sweat on the outside of it, just like your favorite drink on a warm, moist day. It's going to sweat on the outside. We don't want that. So we insulate that to prevent that so we don't get a bunch of water dripping down on the mechanical room floor and having to squeegee that or put a drain nearby or creating some safety hazard and rusting out, you know, the paint on this eventually after years and years of that operation. So we prevent that by insulating it. All right, so those are the 4 types of compressors that you'll experience within the HVAC industry. Okay, let's put this all together here now. So here was that water-cooled chiller that we just saw in the previous slide. We have the evaporator barrel, we have the condenser barrel, and here's our compressor, our centrifugal compressor. And the purpose of this is to produce chilled water. And so we're going to produce chilled water to circulate that chilled water with a pump to either fan coils or air handling units. And then we have a cooling tower here too, we'll talk about in a minute. So all of these components we talk about within that HVAC basic parts video. So again, make sure to watch that if you're not familiar with these. So let's start here at this state. We've got water coming out of this evaporator barrel at a very cold temperature. It's given up its heat to the refrigerant within here. We'll talk about what happens to that heat here in a second. But that cold water now is able to circulate in the system and go to either fan coils or air handling units with coils in them. So this looks like this branches off here and goes to feed this coil. So let's talk about the pathway of the BTUs. And so you're in a room, and there's BTUs being added to it by the sun, by other people in the room, by you yourself, you know, giving off BTUs in the room. Maybe you're exercising, producing a lot of BTUs. Maybe there's lights in there. There's computers on, some other devices, maybe a copier. All those are going to produce BTUs in the room such that it's going to increase the temperature of that room. So a buildup of BTUs is called heat, increasing the heat just the heat capacity in that room, which causes the temperature to increase. And then as it does so, we want to cool it off. We want to accommodate that with cold air. And so we're going to pull that air from that room through that, and it's going to give up those BTUs that's in that air into this coil. It's going to jump from the air into that coil because it sees, that's 40-degree water. Great, I love that. And so the air that comes out of here now, this supply air from this air handling unit is nice and cold. We push it down into the space and it mixes with the warm air, and some of that warm air comes back here, and we continue that cycle. And that's how we cool the air. All right, so those BTUs go into this water and it comes back now at a little bit warmer because those BTUs have increased the temperature of that water from 40 degrees, now it's 50 degrees. So those BTUs go into this chiller barrel, this water cooled condenser barrel, and water goes back and forth and it exchanges its heat with the cold refrigerant that's inside the tubes that's inside of this shell and tube heat exchanger. And so it gives up its BTUs to the refrigerant, causing that refrigerant to boil, and the water then comes out colder because it's given up its BTUs, it's given up its heat, the temperature is colder, and it comes back and it's able to absorb more heat to the space that way. What happens to the BTUs? Let's follow those BTUs. All right, so the BTUs are in a state of gaseous refrigerant because that's what the heat did, is it boiled that refrigerant. So now that gaseous refrigerant goes into the compressor. That compressor pumps that refrigerant into a really high pressure, and because of the perfect gas law, it pushes the temperature up to a point where it can exchange heat with the water within this condenser barrel now. So within this condenser barrel, there's some water, and that's how we're going to get rid of the heat that's in the refrigerant. We're going to exchange heat from that high temperature gas to this lower temperature water here. And so the water is going to come in from this cooling tower at 85 degrees. And we'll talk about how this works here in just a second. But if you've seen our other video, maybe you know how that works already. But it's going to come in at 85 degrees from the sump of this cooling tower, and it's going to see this warm, much hotter refrigerant, and there's heat transfer that takes place. And so we're going to absorb the BTUs from that refrigerant, and as such, it's going to heat up that water to 10 degrees or so, from 85 degrees to 95 degrees, and that refrigerant condenses back into a liquid, goes through the expansion valve, comes back into our evaporator nice and cold to be able to absorb more BTUs from the space. But let's follow those BTUs back here. So we need to get it out of the building. So those BTUs now are in the water. We've exchanged the heat from this barrel here. They're in the water, and now we're going to pump that water over top this cooling tower. And the cooling tower is essentially just a big device that maximizes the surface area of water. We're going to spread that water across all of this corrugated material of some type in here that just maximizes the surface area of it, and by doing so it evaporates. And when this water evaporates, it takes heat with it, just like we talked about, the sweat on your skin. When it evaporates, it takes the heat from your skin, it cools you down. Well, this is going to cool down that water, and to even do that better and more rapidly, we'll have a fan at the top here. We're going to force air across all of that surface area of that water to force evaporation at a higher rate. And as we do that, we're going to remove BTUs more efficiently, and that water then correspondingly drops down to this sump down here, kind of like a big bathtub essentially of water. It's kind of a holding reservoir, and it's going to be colder than the temperature up here because we've removed those BTUs. What happens to those BTUs? Well, the BTUs leave out of the top here at a very warm, moist vapor. And sometimes you might see cooling towers in the wintertime. If it's used for some type of process application, you might see these clouds form off these cooling towers. Yeah, you might have seen them if you've driven by some industrial areas. Don't know what it is, but now you know. It's like, oh, that's a cloud. There must be a cooling tower underneath it, producing all that warm vapor that's now condensing into the cold air. It's condensing back into the form of a cloud. That's how the BTUs travel from the air through this coil, through the water, through this refrigeration cycle here into the refrigerant. It boils the refrigerant, goes into the compressor, pumps it up into a really high pressure, high temperature, exchanges those BTUs within our condenser barrel. We get rid of those out of the refrigerant into the water. It goes out of our cooling tower, and that's how we get the BTUs from inside of our space to outside of our space within a water-cooled hydronic system. Whew, that was a lot. But imagine yourself as an air molecule, or think of it as a BTU, molecule. Again, BTUs aren't really molecules, but think of that pathway of a BTU riding through all those different processes. And I think that could be fairly intuitive for you to make sure that you understand how the BTUs leave the building that way. All right, last slide, let's talk about heat pump operation. So a heat pump is a generic name for an air conditioner. An air conditioner is a form of a heat pump. Heat pumps basically are a device that pumps heat from one location to another. Usually we think of it as an air conditioner that's going to pump heat from the inside of the building to the outside of the building. But it could be reversed, and in the reverse type of a situation, which is usually what we refer to as a heat pump in heating mode, that's the same refrigeration cycle, it's just in reverse, so that these coils are going to reverse their duties essentially. And that's how we're going to pump heat from the inside, and we're going to pump it to the, from the outside, we're going to pump it to the inside that way. So let's think about that real quick. Talk about a couple of temperatures. Again, same refrigerant, and the refrigerant is so efficient. Again, it boils at a low temperature. If the outside is 50 degrees or so, yeah, we can pull heat out of that because the refrigerant is at a very low temperature. We want that to boil. We want that to boil at a very low temperature. So we're going to pull the heat out of that 50-degree air, and then we're going to pump it into a very high temperature gas, and we're going to dump that heat into, by the power of the fan pushing across this coil here, we're going to push those BTUs into the air. There's going to be heat transfer that takes place within our colder environment air. Maybe it's 60 degrees. The returner comes back at 60 degrees. There's going to be heat transfer that takes place with our hot refrigerant and that colder air. And so our supply air now is going to come out at a higher temperature, and that's what's going to be, that's what's going to allow us to heat up our space that way. So because of the temperature of this refrigerant here and the outdoor air, you can imagine that as that outdoor air temperature gets below 50 or 40 or 30 or 20 degrees, it's not going to work too well, because at that point there's just no temperature difference between our refrigerant and the ambient air, and so that refrigeration cycle is going to cease to work at some temperature, at some outdoor air temperature. And so at that time we usually require an auxiliary heater, just an electric heater within our air conditioning unit. And that's just kind of like a toaster coil type element that just heats up, gets red hot, we blow air across it, and that is how we achieve heat at that point to heat the space when it's really, really cold outside. Not very efficient that way, because straight electric heat used in that way it uses a lot of energy, and electricity is pretty expensive. It's more expensive than gas for the same amount of BTUs. But the refrigeration cycle can be really efficient if the outdoor ambient temperature is a little bit warmer that way. All right. I just wanted to cover the refrigeration cycle and how that works, but we could really get into efficiencies of electricity and gas and heat pumps that way, but we're going to reserve that for a different video. Or you can look at that, you can look at efficiencies between gas and heat pumps and straight electric heating and cooling, or electricity used in cooling to produce a refrigeration cycle. I just wanted to make sure that within this video, the basics of you plug something in and how does that refrigeration cycle work to produce cooling. That was the goal of this video, and so hopefully you understood that. If you watched this video again just on a direct YouTube search, make sure to pop over to our website. There's a great assessment there that you can find, and just take that assessment to test your learning, what you gathered out of this. You want to make sure that you score 100% on that. It's not hard, it won't take long, but if you didn't score 100%, or if you were doing your email on the other screen here, you know, really want to make sure that you get the most out of this time and this stays with you. You get retention of this video for a long time. So take that assessment. If there's any parts to that assessment that you didn't get, just Google the question perhaps, or come back to this video and fast forward to that section and get it again, because this is really important as a basis to understand this if you're new to the industry, to understand the different HVAC systems eventually and where that refrigeration cycle is within those different HVAC systems. If you liked this, and if it's something that you want to incorporate at a larger scale within your organization, maybe with some more one-on-one attention and have a Q&A session, please reach out to us at MEP-Precon.com, and we can discuss more personal, either virtual or in-person training on this subject and a variety of other subjects. And be sure to check back here at this YouTube channel often and on our website. We're always going to be putting on more material to help get you smarter and get you up to speed as quickly as possible to be more valuable to your employer and to your customers. All right, thank you for watching. Catch you in the next video.